I'll talk about it more in the context of Argos. So just for those of you who are not aware, I'll go through this relatively quickly. There's an astrophysical phenomenon known as fast radio bursts. The first kind of established example of this is called the Lorimer burst. This is a very short duration radio flash that was seen by the Parkes telescope and published back in 2007. And we've learned in recent times that these very short duration radio flashes come from very far away, from extragalactic distances. And this is what such a signal looks like. This is a very famous plot. You'll see it on Wikipedia as well. It shows the Lorimer burst showing the signal strength as a function of both radio frequency and time. The kind of diagonal black stripe through this diagram is showing us the millisecond duration radio burst as it's sweeping to lower frequencies at later times. This effect is called dispersion. I'll explain a little bit more later, but effectively this dispersive effect allows us to measure the distance to the source. We can account for some of this dispersive delay from the material that's in our own Milky Way galaxy. And then on top of that, we see this extra delay, which is telling us that the source is not coming from our own galaxy, as in the case of radio pulsars, but it's actually coming from galactic distances. I think there's maybe someone who needs to mute because I hear a lot of banging in the background, and I don't think it's coming from here. So we've established that these fast radio bursts come from extragalactic distances. They're hence much more luminous than radio pulsars. And just to quickly summarize, these signals last for a very short amount of time. They last for 100 times shorter than the blink of an eye. And in fact, some of these last for even much shorter than that, more like 100,000 times shorter than the blink of an eye. So you need to record the data at very high time resolution to detect these. We know that they're coming from galaxies that are at millions, if not billions, of light years away. In fact, there was a paper last week that demonstrated one fast radio burst coming from 8 billion light years distance. And in this amount of time, they're emitting essentially as much energy as the sun emits in a single day. And you might be led to think, well, this must be a very exotic, rare phenomenon. But in fact, at the same time, these bursts are happening very abundantly. So it's kind of like a fireworks display on the sky. We see a fast radio burst, or we could see a fast radio burst every 10 seconds from some direction on the sky. But of course, given the limitations of our current radio telescopes, we're only detecting a very small fraction of these. But there's a huge population of these radio signals out there that we could access if we had wide field sensitive radio telescopes to do so. And to put this in context, what's really amazing is these bursts last for 100 or even less times shorter than the blink of an eye, and they're traveling over hundreds of millions, if not billions of years. And if you think about, all the things that have happened on Earth in that time, life crawled out of the oceans, it evolved, we had the dinosaurs, we had the rise of the mammals, etc. And all of this stuff has been happening in the time that this very short duration burst has been traveling from the galaxy in which it was created to the Earth. And then we managed, to point our radio telescope in the right direction just at the right time to do this signal justice and detect it. We're not so sure what fast radio bursts are. There's some theories that are maybe more plausible than others, but there have been over 100 or so that have been proposed. And one of kind of the main theories, this is kind of an overview of the various theories just shown graphically. One of the main theories is that at least a large fraction of them are potentially coming from magnetars, which are these hypermagnetized neutron stars. They're powered by the decay of their magnetic fields. And to some degree, this hypothesis has been confirmed with the detection of very bright radio bursts from a galactic magnetar. So a magnetar in our own galaxy that produce bursts that are approaching the same luminosities that we see from extragalactic fast radio bursts. So we think at least some of these are coming from magnetars. I think what's potentially in the long term the most interesting aspect of this field, though, is the fact that these sources of short duration radio flashes are really excellent probes of all of the ionized material and magnetic field between stars and galaxies, kind of otherwise invisible universe between stars and galaxies that is briefly illuminated by these radio waves traveling between galaxies and stars. And so in the long run, I think there's going to be a whole industry of using fast radio bursts to study ionized gas, and this is because the radio waves are very sensitive to this gas and magnetic field along line of sight. I already mentioned the dispersion effect. So the fact that the light travel time is frequency dependent. This allows us to measure the total electron column density along the line of sight. We can measure effects like scintillation and scattering, which tell us about the distribution of that material, how clumpy it is along line of sight. This is very interesting, for instance, for understanding the interplay between the intergalactic, circumgalactic, and interstellar media of galaxies, how galaxies grow with time. And we can also measure Faraday rotation effects, which give us line of sight magnetic fields. So FRBs are really unique probes of these various topics. And in the last decade or so, a number of radio telescopes worldwide have made a huge increase in the number of fast radio bursts that we know of. In particular, the CHIME telescope in Canada is detecting a few of these signals every single day because it has such a wide field of view. So, the number of sources that we know about has rapidly increased. We found out that some of these signals actually repeat as well. So some fast radio burst sources are not just seen once, although the majority are. Some of them are seen multiple times from the same direction on the sky, from the same distance, so coming from the same source. And this has also taught us, and this is consistent with what I was mentioning before about the magnetar model, that some of these sources are coming from some kind of central engine, some kind of source of energy that is longer lived. So whereas some theories have postulated that perhaps some FRBs come from one-time only explosions, we know that certainly some of them come from longer lived sources of energy. Now, most pertinent to this particular talk is the fact that to understand what fast radio bursts are and also to use them as precision astrophysical and cosmological tools, one of the things we really need to do is we need to localize them very precisely. Because only by localizing them very precisely can we actually figure out which galaxy they're coming from. That allows us to establish their distance through the redshift of that galaxy. And also leads to other interesting applications, including the gravitational lensing effects applications that you'll hear about in the next talk. So we really want to be able to localize these sources very precisely. That requires a radio interferometer. This toy example gives you a feeling for the problem. Even a large telescope like the Arecibo telescope, it had a 300-meter diameter, but the kind of resolution on the sky was a few arc minutes or so, and there are many galaxies within a few arc minutes on the sky, at least if you go out to very large distances. If you can do this kind of localization, you can learn a lot about the source. This is a very well-known example where the first repeating source of fast radio bursts was first localized with a very large array to about arc-second precision. Then it was localized subsequently with the European VLBI network to milli-arc-second precision, and that allowed both the determination, as I was saying before, of the host galaxy's redshift, as well as even more detailed observations using the Hubble Space Telescope that really zoomed in on the galaxy. They allowed us to see that the source is actually co-located with a region of star formation, the host galaxy, consistent with the idea that it has originated from a quite young star or stellar product, like a neutron star that is still rapidly spinning or highly magnetized. So this is one famous example. That's for a repeating source, but there's been a large effort in the last decade to get this to work for non-repeating sources as well. So two of the telescopes that are doing this are the ASCAP telescope in Australia, an interferometer with a wide field of view and good angular resolution. The DSA in the United States is also doing this. The Meerkat telescope is able to localize sources to arc-second or better precision, and also the CHIME telescope is expanding with some outrigger stations to be able to do sub-arc-second localizations as well. Now, what we have been doing here in the Netherlands and in other countries in Europe is we've been using all of these sources that the CHIME telescope has been discovering because of its very large field of view, and we've been targeting the sources that are repeating. So we've been looking at sources that we expect will produce another burst, and we've been targeting them with the European VLBI network because this network of telescopes can provide kind of the ultimate precision that we can achieve in localization. And I'll explain why we want to get to such precise localizations in a second. So to put the problem into context again, one starts with a localization with, for instance, the CHIME telescope as it currently exists without the outriggers, which is comparable to some fraction of the full moon on the sky. So it's maybe a few arc minute precision, depending on whether the CHIME telescope is recorded baseband data. Within that region of sky, there are many potential host galaxies. In this image, you can see a number of foreground stars. There are also some galaxies here. And if we use VLBI, if we use, instead of a single telescope, if we use hundreds, if not thousands of kilometer baselines, then we can zoom in to an area on the sky that is a factor of a few billion times more precise. And that was what was done in this particular case. So using the European VLBI network, it was possible to zoom in to kind of arc minute level precision on the position to milli-arcsecond precision to localize the source not only to its host galaxy, but to exactly the stellar neighborhood that it is in that host galaxy. And this can be taken even farther. So using, again, the Hubble Space Telescope, it's possible to fully utilize that kind of precision, astrometric precision you get from the VLBI localization to match that with comparably, but still not quite as high resolution optical information. And in this particular case, one can see that the source is very close to local star formation. So on the right-hand side here, you can see the source. This little blue dot is essentially the localization and precision on the localization from the European VLBI network. And then you can see in the Hubble image that there are a number of knots of star formation that are nearby, but the source is demonstrably offset. So that leads to some interesting scientific questions about why it's not directly associated with the star formation and why it has this small angular offset. More recently, this is another great example, the CHIME collaboration, they discovered a fast radio burst source, which is comparably very, very nearby compared to the majority of these sources. It's at only a few million parsecs away. And it appeared to be located or hosted by the very famous M81 galaxy. This is a grand design spiral galaxy, which is in the nearby universe. You can see this image of it here, and you can see famous Dutch astronomer Jan Oort standing in front of a picture of the host galaxy here. And using the CHIME telescope, it was possible to localize the source to an area kind of in the outskirts of the galaxy. But with arc minute precision on the localization, it wasn't really possible to figure out, what is at that location. It seemed like it was off in the middle of nowhere. Now, again, with the European VLBI network, we were able to localize the position to milli-arcsecond precision. And what's being shown here on the right-hand side, this is a Subaru image of the field where the FRB has been localized to. The red dot shows you the localization there. And there's a zoom in the top right here. And what's at that location? Well, it turns out instead of being a star forming region like I've been showing you in the previous two examples, it turns out that the source is co-located with a globular cluster. And this is quite surprising because globular clusters are famous for being kind of stellar graveyards. They're not the place where new stars are being born through core collapse. They're not the place where you expect to find massive stars. They're not places where you expect to find core collapse supernovae. Or young neutron stars, unless you can form these neutron stars or compact objects through more exotic formation channels, like, for instance, the merger of white dwarf stars or the accretion-induced collapse of a white dwarf, for instance. So yeah, this kind of put a spanner in the works in terms of thinking, well, maybe all of these sources are young magnetars formed through core collapse. If this is a young magnetar, then it had to have been formed through more exotic scenario like I just described. So these are some examples of, not only looking at the sky at basically the highest time resolutions that we can achieve, but also at the highest angular resolutions we can achieve, and building towards the future and thinking about how Argos comes into the picture here. I think, well, as I'm gonna argue on my last slide, I think, to really make interesting progress in radio astronomy, we need to be thinking about expanding the observational parameter space that we're searching, and I think we need to be thinking about as much as possible, pushing to the extremes of resolution in every possible dimension. So highest possible time resolution, highest possible frequency resolution, highest possible angular resolution, et cetera, et cetera. I think this is where we're going to make the next, amazing discoveries that are similar to fast radio bursts in terms of, being unpredicted, but being really scientifically very, very informative. And towards the future of fast radio bursts in particular, I think we want to not only find them, I think we want to localize them to milliarc second precision using interferometric arrays that can achieve this. And we want to couple that with the future optical telescopes that we're going to have, not just HST and JWST, but quite interestingly here on the ground, the European Very Large Telescope, the ELT, which is in construction and which in principle can provide also milliarc second precision astrometry and enough sensitivity that we can detect massive stars and resolve stellar populations in other galaxies at the distances that we detect FRBs to. So I think there's a huge scientific opportunity here. Beyond Europe's role already and using existing infrastructures like the EVN to make these very precise localizations, I think what's been really rewarding in doing this type of work is you can see how it builds up local capacity within research groups that have maybe been doing more traditional VLBI, more traditional interferometry. They're now getting interested in doing this at a very high time resolution. So we've established, for instance, collaborations with groups in Poland and Sweden and in Germany to do this kind of work where we're pushing the boundaries both in terms of time and angular resolution at the same time. And this is kind of breathing a new life into these infrastructures as well. We have these 25-meter class radio telescopes at these sites that have been doing excellent work as part of an interferometer, but they're also doing very interesting work by exploring the time domain now, right? So to try and bring the whole picture together, I want to also briefly introduce LOFAR. And I think many of you have probably heard of LOFAR before, maybe some of you haven't. Just very briefly, LOFAR, just like the EVN, is a pan-European telescope. It's also a VLBI telescope, essentially. It started as a Dutch telescope, but with the adoption of international stations, the International LOFAR telescope now is basically a low radio frequency VLBI telescope. It operates in real time using fiber networks across the continent with 10 gigabit per second connections. It's unlike the EVN is operating using much lower radio frequencies. So two different types of antennas, these low band array antennas and high band array antennas. And these together offer a view of basically like the lowest octaves of the radio window that we can see from Earth. And this complements the type of work that can be done with higher frequencies with telescopes like the European VLBI network. And importantly, LOFAR is offering us not only a VLBI instrument, it's offering us a VLBI instrument that has very high field of view as well. So this is an example of a LOFAR image where you can see that you're kind of getting the best of both worlds. You're getting an image that has about 20 square degrees of sky. So this is the moon for comparison. You can see that there are tons of sources, galaxies in this field of view. Right at the center, there happens to be a galaxy cluster, which is called the toothbrush cluster because it kind of looks like a toothbrush here. So you can see that you're getting great field of view. You can do fantastic surveys. This is also very good for transients because you're capturing a large fraction of the sky at any given time, and you can just sit on the sky for a large amount of time, and you're getting the angular resolution to do interesting studies as well. And this is just an example of the kind of angular resolution that you can get from going from the LOFAR Dutch baselines to the international baselines that the telescope offers. So it makes a huge difference in the type of science that you can do when you can actually resolve these sources. Now, the LOFAR telescope is currently being upgraded. Pretty major renovation, about 20 million euro investment in the telescope. What we've done is we've taken the LOFAR stations that currently exist. Each of the fields has a number of antennas attached to it, low band antennas and high band antennas. And these are combined into a single coherent telescope at each one of the stations using processing power at each one of the stations. And in a very similar way, this forms kind of a single coherent telescope, just like Argos will be doing as well. at each one of the stations, and the station signals are obviously combined across the Netherlands and across Europe. Now, at the time that the telescope was built, only about 12 years ago, computational capacity at each one of the stations was really a pretty major limitation. It was only possible to use half of the antennas at any given time, and hence, a fraction of the telescope was just kind of sitting there and not being used at any given time. With the LOFAR 2 project, we're expanding the stations to have an order of magnitude more computational capacity, and it will make it possible to use all of the antennas all of the time, both the low band and high band simultaneously, and all of the low band antennas that happen to be there. And one of the next things that we want to do to expand the LOFAR array is to increase the fiber network that's connecting to the stations, because now by increasing the computational capacity at each of the stations, we're able to do much more with the antennas that are already there. But now we're limited by the network connections between the central computing cluster and the stations. That's currently, as I said, 10 gigabit per second connections. The state of the art now is more like 100 gigabit per second or a few hundred gigabits per second. And by doing that, we'll also be able to expand the field of view of the telescope. We'll be able to bring back more information from each one of the stations. And I would say in general, what do we have in Europe? What are our strengths in Europe in terms of radio astronomy? Well, I think both LOFAR and the European VLBI network, they are demonstrating that we're entering a new regime of radio astronomy, whereby using relatively cheap local antennas and using high-speed fiber networks and large computing infrastructures, we can create telescopes that are able to offer enormous angular resolution, very large field of view, can operate at very high time resolution as well. And we have not reached the logical limit of this. As I said, by upgrading, for instance, the fiber connections for LOFAR, we can do much more with the antennas that are already there. It's becoming more and more easy to spread high quality frequency and time standards from a given reference maser to different stations. This is something that's being implemented in LOFAR as well. Something that the EVN has demonstrated as well, using, for instance, the maser in Westerbork has been transferred to the old Dwingelo telescope, which is 20, 30 kilometers away, to get fringes between those two telescopes. And in general, we in Europe, we have this huge infrastructure of radio astronomy sites. We have local groups that have local radio astronomy infrastructure and local expertise. And in the context of Argos, what I think is a really interesting idea to explore in more detail is, the original concept of Argos is a collection of antennas with relatively short baselines in Crete. If we really think creatively about the infrastructure that we have in Europe at the various LOFAR sites, at the various EVN sites, and we think about the value that they have in terms of local expertise, in terms of fiber connections, et cetera, and land, for instance, as well, then we can really think about how do we expand on what we already have in terms of LOFAR and the EVN, and also the work that's going into Argos, the work that's going into radio blocks, for instance. How do we leverage all of those things together to create a pan-European array of radio telescopes that spans not just LOFAR and EVN frequencies separately, but maybe together, that gives us sub-millisecond time resolution for some of the nice transient work that I was explaining, gives us much larger bandwidths, because if we have larger fiber connectivity to these stations, we can also be operating over larger radio bandwidths, increase the field of view, and do all of this at milliarc second angular resolution. And I think in the increasingly rich landscape of radio astronomy that is emerging, and thanks to a large part due to the coming of SKA and all the precursors and pathfinders that have been created for that, I think it's still possible to create a unique instrument, something that will complement what will be possible in the future with DSA 2000, that'll complement what will be possible with the Chime outriggers, will complement the SKA, and can also connect to these telescopes as well. And I think what for me is very motivational about this is not the fact that we're just reusing some of the enormous heritage and infrastructure that we would have in Europe. I think it's a really fantastic way to build local capacity, to bring in new countries into the European family of radio astronomy. LOFAR has been incredibly successful in building new stations in countries that have maybe not the means to build their own mega infrastructure, but can bring together a few million euros to build a new station. Bulgaria, for instance, is building a new LOFAR station. Italy is going to be building a new station in the next year or two as well. It's a great way to buy into a much larger infrastructure. And Argos should be thinking about this well, I think. If it's possible to create Argos-like stations for something on the order of €1 million, it becomes possible for a university or a small institute to buy into the project. I think, as I said before, the future of radio astronomy requires pushing in every direction of observational parameter space. I think some of the most interesting discoveries in the coming decade of radio astronomy will be made by turning the knob on all of these different parameters basically as far up as you can. If you're familiar with Spinal Tap, basically turn every knob to 11 or so, and then I'm sure that there will be fantastic discoveries that'll come out of that. And I think one of the strengths that we have is also the fact that this type of very long baseline interferometry, the science is very compelling, but also, the political, the social, collaborative aspects of it are very compelling as well. We're living in a world where there are increasingly, stronger borders. There's increasingly more strife in the world, but really this type of science is very literally about building connections across barriers instead of building new barriers, right? It's about connecting, in a very literal sense, different countries together. So I think that's a very motivational, compelling aspect to this as well. That's basically all I had to say. I'm happy to take whatever questions you may have.
So thank you, Jason. So sort of everyone is clapping here, and thank you very much for making the case for this very long baseline Argos stations. And also, just to add a comment to that, I think that might also sort of that eventually in the future that might actually be the only way to go about it, given that also RFI has become a huge problem already for everyone. So.
Yeah, RFI has become a huge problem for everyone. I guess you might say, why would you build a radio telescope in Europe and instead of a radio quieter place like South Africa or Australia? And I think for very long baseline interferometry, you run out of places to build telescopes. You have to deal with this problem head on because you by definition need telescopes in various geographical locations. You need to be building telescopes that can deal with the local RFI in a graceful way, right?
Yeah, but also, I mean, just correlating over long baselines gives you more flexibility to deal with this.
Well, yeah.
Okay. So any questions for Jason? Yeah. So Anna, go ahead. Probably I can just hand it to you. Or maybe you come here because the microphone is here.
Hi, Jason, Sana here. So, hi. So you said about the repeaters. We now have some known repeaters and some others that don't seem to repeat. Just from my ignorance, no, is it clear that they don't repeat, or could it be that maybe they repeat at a much lower sort of volume and we are not able to hear them?
Yeah, that's a very good question because that is a very active topic of debate within the community. I think there's good evidence that a lot of the non-repeating sources are capable of repeating, simply in the sense that kind of the least active repeating sources are not much more active than the ones that we've only seen one burst from. So it suggests that there's a continuum, and that if we observe longer, we'll see them eventually repeat. At the same time, though, strangely, some of the repeaters are really hyperactive. You could look at them for an hour and see hundreds of bursts, whereas others have been looked at for thousands of hours and only ever seen one. So there is a very broad distribution of rates as well. So certainly some of the ones that are non-repeaters are probably capable of repeating, but I at the same time, I would certainly not rule out that some of the ones that have only been seen once will never repeat again and might be just very different in nature. Some of small fraction of FRBs might come from cataclysmic events. That's certainly still possible.
Okay, thanks. That's fascinating. And with respect to when I remember the beginning, the first discoveries, it's great to see how much it has advanced your understanding of those.
Yep. Yeah, and I would say I feel like the field has become richer as well. Yeah.
Right. So, Ewan?
Jason, nice talk, thanks. I missed a little bit of your talk, so maybe you mentioned this already, so apologies if this is a repetition. You know, for bringing in more and more stations across Europe and kind of democratizing VLBI access, how do you envisage standardization across all of the stations, and whose responsibility is it to correlate, and are the standards the correlator's responsibility to enforce, or the observatory's responsibility to enforce? How's that going to look?
Yeah, it's a very good question. So some of you might know already that the current EVN is actually a very heterogeneous telescope. So basically I don't think there are any telescopes in the array that are exactly the same. I think every telescope has its own peculiarities, and that all kind of fortunately washes out in in the mix when the data is correlated. LOFAR is quite different, obviously, because every station is in principle identical. I think what I'm trying to say here is I think it's the case that you don't necessarily need to have a network where every single station is exactly the same. It doesn't even need to be the same type of antennas, as long as they're operating at the same wavelength. In terms of responsibility for correlation, well, the European Joint Institute for VLBI Institute does this for the EVN, but at the same time, the ability to correlate such data is becoming increasingly easy. So we operate actually the EVN in something called the EVN light mode, where we operate the telescope outside of the normal sessions, where they do kind of more standard interferometric observations, and it's possible for us to just correlate those data with a small computer cluster. And in terms of formats, you were also asking about formats. I mean, there are standardized VLBI formats that the data can be packaged in or converted to as necessary. Maybe I'll take this opportunity to actually explicitly say something that I didn't quite say. You know, we had nice talks by Giuseppe, for instance, about radio blocks, and we've heard a lot about Argos itself. One of Astron's future visions for utilizing the LOFAR infrastructure would be to create something, you know, not operating at low frequencies, but probably at higher frequencies. You might, you know, call it HIFAR instead of LOFAR. That's not an official name, but just to call it something. Because yeah, I just want to emphasize again, you know, all of the work that has gone into creating this network of sites where radio astronomy can be done and that are interconnected and then can be operated even in real time as a single interferometer. A very natural expansion of that in the future would be towards higher frequencies, larger bandwidths, and then you really think about stations that look quite similar to Argos. Might not be exactly the same, but same idea. Cheap small antennas, large N, cheap antennas.
So thank you, Jason. Any other questions for Jason? Oh, there's a question online, I think. So the question is, not sure if you can read it, Jason. So there have been no FRB detections below 100 megahertz so far. What might be the reasons behind it?
Yeah,
that's
there hasn't been I would say that there hasn't been an enormous effort to detect them at lower frequencies. But one of the possible explanations is we certainly know that some FRB sources are in very dense and dynamic local environments. For instance, Daniele, who was on the call, wrote a paper about this about 5 years ago, where the first repeater was found to be in a very, well, like I just said, dense, extreme ionized local environment, as inferred from its very high and rapidly rotating rotation measure. And if you think about these sources as potentially very young neutron stars with a lot of material around them, one of the possibilities is that the radio bursts are either absorbed or just very strongly scattered by the local medium or even the intervening medium. So as you go to lower frequencies, unless the radio spectrum is very steep, unless the source is becoming much brighter, there are all kinds of propagation effects that make it harder and harder to detect these very short duration signals. So that's kind of a natural explanation for why we haven't seen them at lower frequencies yet.
And so, okay, so thanks, Jason, again. So